Hello, this is Jay McCarthy from PrimeVault with another of our architecture series talks. In this one, we'll be talking about the main method that PrimeVault uses to secure your keys against attackers and rogue employees of PrimeVault. Recall that many of our competitors only use MPC, multi-party computation, to do this. Whereas at PrimeVault, we use another tool as our foundational layer and offer MPC as an additional layer on top of that. The main tool that we use is something called a hardware enclave. This is going to be a non-technically detailed explanation of hardware enclaves, and people who are familiar with the details of how hardware enclaves work will balk slightly at some of the explanations I use. But I hope that they'll agree that they are sort of directionally correct and they are an appropriate analogy for the real abstractions that enclaves provide. Now, if I were like a normal, casual person talking about computers, um, imagine I've, got my phone in my hand. Perhaps people have this intuition that the way that you know what's happening on a computer is by looking at its screen. And the way that you interact with it is by typing on it, clicking buttons, and so on. And they may not realize, or it may not occur to them, that the information that appears on the screen is actually first existing at an electronic or physical layer beneath the screen. For example, in principle, I could like literally take the chip out of my phone and put it under a microscope, an electron microscope, and put it inside of another device and read the information off of it. Now, no normal person would actually do that because it would be too expensive and annoying to. That's not the way that we like normally interact with our computers. But in principle, such a thing is possible. And it's for that reason that it's so common for computers nowadays to use tools like BitLocker that encrypt the information on the disk. And the goal of encrypting it on the disk is to make it so that when you turn on your computer and you authenticate, you're not merely logging in, but are actually and authenticating yourself. You're actually giving the computer information that it doesn't otherwise have that allows it to decrypt the information on the disk as it is read. So in a situation like that, like me having access to your turned off device before you've authenticated to it does not allow me the ability to read the secret information on it. But what if I have access to your device after you've authenticated? Well, one of the things that I could do is I could put that same, electron microscope that is examined in the memory, I could just point it at your running computation. And yes, maybe use BitLocker to load to decrypt blocks as you're reading from the disk, but they're going to be unencrypted in memory. Because your computer, your programs are going to have access to them. And what if I had a computation running inside of an environment where even physical access to the device would not allow me to read what was going on? It's the goal of an enclave. Now, this physical access to the device can both stand for literal physical access, where I can touch it, I can put it under a microscope and so on, as well as more abstract access. So, for example, what if I could like run a program on your device at the same time as your program? So your program's running something that you want to be safe, your key manipulation program, but it's also running my program. Well, what kinds of ways can my program see what's happening inside of your program? Operating systems intend to provide isolation between processes so that your web browser can't see the contents of your crypto wallet because they're in different processes. But one of the problems that's common in modern architectures are that there are sometimes ways for programs to see inside of each other's memory, both because of errors in operating systems and because of errors in CPUs and library software, and even sometimes intentionally. So this kind of problem is particularly prevalent when it comes to cloud infrastructure, where one program may be running inside of a virtual machine that's running on top of some physical hardware that's running multiple other virtual machines. So the sort of worst case scenario is when I'm running something that I think is secure inside of a virtual machine, but that virtual machine is actually visible to a different virtual machine that just happens to be running on the same cloud architecture. Hardware enclaves, or trusted execution environments, TEEs, are physical architectures of CPUs, motherboards, and so on that are meticulously designed to prevent this kind of cross-process, cross-virtual machine, cross-OS, cross-physical device access. And there are a number of providers of TEs, but one of the ones that we use is the Amazon Web Services Nitro enclaves. What these do is inside of the AWS virtual resources, you can run a second additional virtual machine. And that additional virtual machine runs in this special lockdown mode. It's so locked down, in fact, that it doesn't have access to the network, it doesn't have access to any disk, it doesn't have access to anything except a really small port of communication to its parent, which is called the VSOC interface. And something that's special about these TEs is they can produce what's called an attestation. Basically, an attestation is something that's kind of similar to what blockchains do. It's a blockchain style hash of the code that's running. So in the crypto world, we have this intuition about what a blockchain is, right? The blockchain is we have some data, that's the block, and we run a hashing algorithm which compresses the data down to a small amount of information. So 256 bytes, 32 bytes, something like that. And then this checksum then uniquely identifies that block. And each block references the previous block, so there forms this chain of all the blocks. Well, that same hashing algorithm that compresses the information up at a block can be used on any data. And in particular, what TEs do is they allow that data, the data that's checksummed or hashed, to be the actual memory of the program that's running. And why is this important? What it means is that when you turn on a TEE, it has no way of accessing anything outside. There's no way the outside can ever force it to do anything. The only way that it will do something is if it decides to do it. And so therefore its behavior is deterministic with respect to the initial contents of memory, meaning the initial program that's loaded. So what it does, the very first thing it does, is it computes the checksum of that initial image and identifies it. And so it says, I am running version 1337. And anyone, they can look at the same software and they can run the checksum algorithm again. They can see that, aha, yeah, it really is running version 1337. And I know what version 1337 is. I like it. Now, when I communicate with this program, I know what the program actually is and what it will do. Now, if you're not like deeply in the technical world, this might not seem that interesting to you because you say to yourself, well, I mean, I open up my Venmo app all the time and it says right there, running version 101. What's the big deal? Well, the problem with your Venmo app is that when it says it's running 101, it can lie to you. And hackers, that's one of the main things they do. They lie. They get the software to say it's running one version, but actually be running a different version because saying it's running something is just some text on the screen. You can write a program that prints out anything that it wants. But what's more reliable is actually knowing via cryptographic signatures, for instance, that the software you're communicating with really is one particular version that is uniquely identified by some checksum. In some ways, this is the thing that makes smart contracts valuable, because why smart contracts are valuable is that they're a service online that you can communicate with where you know what the code is. And if you know what the code is, then you can know, for instance, that if I send it an ETH, then it will send me back a certain amount of USDC. And it's that guarantee that's offered by smart contracts on Ethereum. It's that guarantee that's offered by immutability, knowing that when you send a message, it will be heard by code that you actually know what it is. Now, what TEs do is they make it so that the smart contract like guarantee is provided not only on a blockchain, it's provided externally. So now at PrimeVault, we think the blockchains are great. That's why we're in cryptocurrency. However, blockchains, they have some big disadvantages. Like there are certain things we don't know how to do yet on chain, and even some things that we do how to do, they're like really inefficient and they're not flexible. And like blockchains, they have this really constrained execution environment. For example, they have to be public. And like you clearly don't want your secret keys managing your assets to be part of the public computation infrastructure. You want them to be private. And but you still want that immutability and guarantee that blockchain provides. And that's exactly how and why PrimeVault uses TEs to get those sorts of immutability guarantees without the publicity and the constraints. Now, because DEs offer a private way to have a guarantee about what code is running, in the case of PrimeVault, the code that's running is your vault. That's the thing that holds the keys. And the policy evaluation engine that looks at your policy and decides when, where, and how to use your keys. And since we know exactly what version is being run, you can know exactly what version is being run by looking at the attestation document that's generated by the TE. You can see that, aha, oh yeah, it really is running version 13337 and whatever the policy software is. And that hasn't changed since the last time I talked to it, so I know that it's safe and I know that it's really running the right thing. And I know that that software, because of the audits and theorems and other guarantees that PrimeVault provides, is only going to do the things that it's authorized to, meaning that it will only ever use my keys the way that my policy said. Because the code that we actually run inside of this is basically just an agent for you, where you tell it, please do something, consults the policy and sees if that's allowed, and it will never use the key for any other reason. And so this is the main mechanism that PrimeVault uses for security. We have these immutable vaults that hold your secrets, where they're guaranteed to be running particular versions of the software, where that software is constrained to only execute what your policy is. Now, in a future talk, we'll talk about some of the other things we do, but at a high level, this is the main difference between PrimeVault and other custody providers. Most other custody providers, they're relying only on MPC to protect the integrity of only the keys. They make no claims whatsoever about how and whether they protect the policy. Whereas we focus on a new tool, the TEE, that allows us to protect both the policy and the keys at the same time, And we can add MPC if we want as a layer on top of that, thus providing more security and more usability as well. That's all for today. Thank you very much. I'll talk to you soon. Bye bye.